One of the benefits of GitOps in Kubernetes is how it can enable application developers to provision the infrastructure that they need. It enables teams to transition from a more traditional approach where there's over-reliance on a platform or infrastructure team to more of a self-service model. And this self-service doesn't have to be completely void of your platform teams because they're generally responsible for the infrastructure layer. But we want to address the bottleneck that slows down the process of devs getting what they need when they need it. Usually it stems from platform teams being flooded with things like tickets, emails, and messages from other teams that need operational support, like infrastructure changes. Here's an example of a development workflow using GitOps. Application developers can define the infrastructure that they need as code, submit it as a pull request, and a platform team can then review that pull request. Upon approval, they could merge it into a branch that your GitOps operator is watching. The GitOps operator will then compare this to the live state, detect any differences, and automatically reconcile the state based on the declarations in the repo. As a result, the infrastructure change control process to Kubernetes is automated and primarily driven by the developers. But there are a few other things that we have to consider. How do we create a simple, automated, and consistent workflow for development projects in this self-service model? And how can we provide enough flexibility but still control the parameters that developers can operate within in the self-service approach? To address these issues, we can use ArgoCD's ApplicationSet. But first, let's define what an application is in ArgoCD. An application in Argo defines the source and destination for your Kubernetes resources. The source is the location in a Git or Helm repository where your Kubernetes resource manifests live. The destination is the location where the resources should be deployed in your Kubernetes cluster. Now, in a real-world scenario, an organization could easily end up having multiple ArgoCD applications, whether that's hundreds or even thousands. And it can become an administrative nightmare and a challenge when trying to achieve some degree of consistency across your applications. And that's where the ApplicationSet controller can help. The ApplicationSet controller can be used to automatically manage the lifecycle of your ArgoCD applications. A controller's job in Kubernetes is to continuously watch and make sure that the live state of its resources matches the desired state. Now, the ApplicationSet resource allows you to define a template from which other applications will be created. This resource is powerful because it provides a great deal of flexibility. The ApplicationSet resource contains parameters that will be substituted by the values required for the applications that are being created. To insert these parameters, we use generators. As the name implies, generators are responsible for generating the parameter values that will be inserted into the application templates. And there are different types of generators, but I'll be working with the Git generator for this particular workflow example. The Git generator will allow me to create ArgoCD applications based on files stored in a Git repository. This repo will be watched by the relevant ApplicationSet resource. It will function as the data source for the values being generated into the application templates that the ApplicationSet is managing. But we gotta ask, what does that look like in this self-service development model? Well, for starters, a platform team can own and create the application set that will manage all these applications. The application set will define the template for the infrastructure that development teams will be creating through GitOps. As for the development teams, they can create the configuration files that will function as the data source for the application set. These config files will contain the values that will be inserted into the templates. Each config file will essentially trigger the creation of a new application by the application set. The dev teams can then send a pull request with that specific config file, and when it gets merged into the branch that the application set is watching, the application set will pull those values and automatically create an ArgoCD application with values generated from the config file in Git. Now I'm going to demonstrate this with an example of how developers can manage the creation of their own Kubernetes clusters and deploy applications to them. Both processes will be carried out using GitOps, and specifically managed by ArgoCD's ApplicationSets. Instead of provisioning separate EKS clusters, I'm going to work with a single host cluster where ArgoCD will be deployed, and developers can then create their own virtual clusters that will run on the same host. Such an approach provides a scalable and cost-effective foundation for multi-tenancy in a dev environment. vClusters offer the same strict isolation that an entirely separate cluster would offer, except this is a cheaper model, and because vClusters are light, Your EKS host can house a number of them. And this approach also allows you to share the cluster resources that would otherwise have to be set up and managed independently in the case of running separate fully fledged clusters. More importantly, developers can have an isolated space for freedom, experimentation, and velocity in their projects. And when they need to implement an infrastructure change, whether it's creating, updating, or deleting, they can manage it themselves through GitOps.
All right. As I mentioned previously, this demo will focus on how developers can be empowered to create their own V clusters, as well as set up the continuous delivery for applications to those V clusters. And all of this will be done using ArgoCD. I'm going to create 2 V clusters for 2 different microservices, orders and products. However, I'm not going to go through the process of creating pull requests and then eventually merging those PRs into a specific branch. Reason for that is the config files are already merged into the repository in the right branch that the ApplicationSet resources will be watching. But the ApplicationSet resources haven't yet been created. Instead, I'm going to run a script towards the end that will automate the process of creating those specific manifest files, and then ArgoCD will essentially go to work because the right data sources for those Git generators are already in place. Now, as I like to do, I'm going to start with a code walkthrough so that you're familiar with the different pieces bringing all of this together. I already have my ArgoCD application running inside of an EKS host cluster. And then I'd also just like to show you the directory or folder structure for the specific repository that is being used in the Git generator for the different application set resources. So what we have over here is a folder called cluster and app config because it houses the configuration files for both the applications and the clusters. Engineering is what contains the configurations for the applications or microservices. And as I said, I'm working with examples for orders and products. If I click on orders, you'll see that we've got a config.json file. And we'll take a closer look at that in a short while when I do the code walkthrough. And similarly, under V clusters, we've got orders and products, and each of them also contains a config.json file. Remember, the config.json file is all that the developers would be concerned about when it comes to this entire workflow. All right, now let's get to the code, and I think a lot of this will become clearer to you. So first off, we'll look at the application set that will enable developers to create their own V clusters. Now, this resource is destined for the ArgoCD namespace, as you can see over here. And in addition to that, you can see that under the spec configurations, I'm specifying that it uses a Git generator. And I also detail the repository, the target revision for this repo, and its file path. This file path means the ApplicationSet resource will watch for any config.json files in the particular directory path that I've specified. And you'll see that this correlates with what I have in my Git repo that I just showed you. All right. So if you think about the pod template section in a deployment resource, well, this is very similar to that. ArgoCD ApplicationSets also have a template section which is used for creating ArgoCD applications. Now, the properties that are wrapped in curly brackets, as you can see over here, these are the template fields that will be substituted with the values from the config.json files. Now, your platform team can use this as a way to determine how much control developers actually have. For example, with this resource, developers can create a config file with values that determine the name of the ArgoCD application and the project that the ArgoCD application will live in, among other things. Now, remember, an ArgoCD application is all about setting up the source and destination for ArgoCD. In this case, the source is a Helm chart. And if I just scroll down a little bit so we can focus on that section, you'll see under source, we've got chart, and it's using the V cluster chart. And I'm also specifying the relevant repository and the specific repository where the V cluster will be pulled from. And I've also statically set the version of the chart so that it's standardized for all developers, because generally they shouldn't be able to modify that. You want to have some form of consistency. Of course, if you want to change that, you would simply change this into a template field. And right at the bottom, we've got our destination section. And in this case, it's dynamic, but it could also be static to avoid developers making the mistake of deploying a V cluster to the wrong host cluster. and to the wrong namespace. I'm going to scroll up a little bit over here. You'll also notice that I have some additional Helm properties for my release, such as the specific K3s Kubernetes distro that I want to use. I've specified that over here. I'm also specifying that I don't want to make use of persistent storage in my virtual clusters, but you should obviously understand the implications of doing that. And if I come down a little bit here, you'll see I've got a bunch of different init manifests. Now, the first init manifest over here is me creating the namespace where my microservice application is going to live inside of the V cluster, which is e-commerce namespace in this case. And then I'm creating another namespace where all the ArgoCD admin resources are going to live. And then below that is where I'm creating my service account, my cluster role binding, and these are particularly important in order for ArgoCD to be able to manage your virtual cluster and actually deploy applications to it. So let's talk about some of the things going on over here. I'm creating a service account and attaching it to a cluster role binding that references the cluster admin cluster role in K3s. Now, the creation of a service account will automatically generate a service account token, which will be needed later on, and I'll come back to that. Now, once again, this is for the platform team to manage. So what do developers have control over? Well, that would be the config.json file, as I mentioned previously. Each of the properties in this file correlates with the template fields in the application set. H cluster stands for host cluster, in case you're wondering why I called that H cluster. And then V cluster is for the virtual cluster. Now, as soon as this file is merged into the appropriate branch, the application set will automatically create an ArgoCD application with these values. The ArgoCD application will then create the connection between the Helm repo source and the EKS host cluster and deploy the orders V cluster to the appropriate destination with all the properties that I specified. Now, any other development team would just have to create another config file. And once it's merged into the right branch, the process would work in the same way. And I have another config.json file over here for the product virtual cluster. And in order to create another virtual cluster, I would just create another config.json file and merge it into the right location. Now, remember I mentioned that I've already got these config files merged into the appropriate branch when I showed you earlier on that Git repo, but the application set has not been created. But when I do that later on, everything else will be automated. All right, so that's the virtual cluster application set. Next up is the application set for the applications that will deploy the actual microservices to the V clusters. And I'm not going to spend as much time on this one because I've covered most of the details about how it works in the previous application set. But you can see that this application set is using the same Git repo, but a different file path. This time it's looking for config.json files in the engineering directory. And I showed you that earlier when we looked at the Git repository that contains our data sources for these Git generators. Now, this is the directory where developers will look to merge config files for the application sets to act on. This time, the application template, though, has a Git source. So if you look under the spec section and under the source, it is not using Helm. Instead, it is using a Git repository. And this Git repository actually has a Helm chart for the application inside of it. Now, if we look at the orders config file, I'm going to come over here. You'll see that the V cluster property, right at the top section, has the details of where this application should go. And we've just set up owner over here to be for self-documenting purposes, which is one of the things that infrastructure as code is really good for. So we know who the owner of that particular virtual cluster is. As for the address, in case you're wondering where that comes from, when a virtual cluster is created, it will expose a particular service. And then all of my virtual clusters are running inside of a namespace on the host cluster called vCluster. So the service that gets created is called orders vCluster. That will be automatically created. You don't need to worry about that. And this is running, remember my vCluster is running inside of a namespace called vCluster. And so If we were to look at the products vCluster, you'll see that it has a very similar structure. And you'll see similarly exposed, the virtual cluster is actually exposed on a service called products vCluster, and it's inside the vCluster namespace. Lastly, we come to the automation script. And as I mentioned earlier, this would not be part of the development workflow. I've simply created it so that I don't have to create PRs, approve, and then merge them. But let's go through it so we can see what's happening over here. First, I connect to my EKS host cluster, as you can see over there, and then I create the namespace where all vClusters will live on the host EKS cluster, which is named vCluster, and you'll recall that I mentioned that when I was walking you through the config JSON files for the microservice applications. And after that, I am creating the first application set, which is managing applications for vClusters. Once the vClusters are up and running, I need to add them to ArgoCD. So this sleep over here for 2 minutes is just to wait for the vClusters to actually come up. It doesn't actually take 2 minutes. It's a little bit less than that, but just want to be on the safe side so I don't run into any issues. And now over here, as I mentioned, we need to add the vClusters to ArgoCD so that Argo can actually manage them and send deployments to them. If you recall, I spoke about a service account token that gets generated. Well, that token actually gets stored as a secret inside of the virtual cluster. And that token is what is actually needed by ArgoCD. And so I'm actually going to run a command that will fetch that token and then populate it in what is known as a cluster secret. Cluster secrets are applied to ArgoCD so that Argo can use the relevant credentials to authenticate against the API server of any cluster that it is managing and deploying to. Now, if you're wondering, where am I getting this supposed Helm template from? Well, I have another folder at the top over here. I haven't included it in my repository because this is very arbitrary. You could definitely have a different approach, but I have a Helm chart over here, and I'm going to open up values and templates because that's what's really important. And you can see the template for the cluster secret, and you can see this is going to be applied to the ArgoCD namespace. And then the secret will be prefixed with the name of the virtual cluster. And then very important over here is the server should definitely correlate with the virtual cluster that ArgoCD should be managing or communicating with. You'll recall that these are details also in the config.json file, and all vClusters live in the vCluster namespace. Then under config, specifically the bearer tokens section, this is where the ArgoCD admin service account token is going to be populated. So I'm going to close that template, and just so you can see the values file, these are the values that will be used in that particular template. I'm going to collapse this and come back to the creation script. And so you'll see I'm running a Helm template command against that particular Helm chart. And so what I'm doing is I'm then going to populate the relevant values. So you can see I'm setting vCluster name using the name of the virtual cluster. It's just a variable that I set over here. And then for the admin service account token, that I'm connecting to my virtual cluster and getting the secret for the particular service account token. And you can see over here, I'm specifying that data token. And once that is fetched from the relevant place, I am outputting a YAML file, which is essentially going to be the name of the virtual cluster.yaml. And I repeat that process for the second virtual cluster as well. And once I have those, the last thing that I need to do is essentially just apply them to the ArgoCD, to the EKS host cluster where ArgoCD is running. Once that is done, ArgoCD will connect to these clusters, and then the last thing that I do is then proceed to deploy the last application set. The reason why that's important is ArgoCD needs to be able to first connect to those virtual clusters before it can attempt to deploy my microservices to them. And so once this application set is created, it will go through the process of deploying those microservices. And that brings things full circle. What we can do now is test this out, and I'm going to run the automation script. Once my automation script is complete, I can see the results inside of ArgoCD. And as you can see over here, I've got both virtual clusters that have been created successfully. And in addition to that, I've got the respective microservices deployed to the right destinations. Orders is running inside of the Orders V cluster, specifically in the e-commerce namespace, and the same goes for products. It is running in the products virtual cluster and specifically in the e-commerce namespace. If I was to click on this over here, I'd be able to see the relevant resources that are running from the service account, the deployment that is controlling the respective pods, etc. And you could narrow down things even further with role-based access control to ensure that only the right people or teams are able to see the application or cluster that they should be able to see. Now, the next thing is, how do we actually connect to our application that we are working on as a development team? Well, once you're connected to the EKS host cluster, you can then connect to the appropriate virtual cluster using the vCluster CLI tool. And I'm going to run the command here, vCluster connect orders vCluster, which will connect me to that specific one. I'm just going to hit enter over here, and this will essentially port forward me through to that cluster. Now, if you follow this approach, you will just have to keep this particular terminal tab running. And there are other ways that you can connect to your virtual cluster. Once we've done that, the next thing is to port forward to the appropriate application, in this case, orders. I'm going to hit enter over here, and this will port forward me through to that application. And once that is running, just going to come here to a tab and hit enter. And I can see my orders application running inside of the virtual cluster on the EKS host cluster. So I hope that was helpful. Provide some feedback in the comments. Once again, you can definitely modify this workflow or approach to something that's more suitable for you and your team, but I hope you were able to connect the dots to see how it allows you to create a self-service model for your Kubernetes development where application developers are able to easily provision their own infrastructure using GitOps.